It's a long unit. It has lots of graphical data. And to be honest with you, if I were a first year student, I would not read it from cover to cover. I'm not required to, not from an assessment point of view, nor from a knowledge point of view. You can do it very smartly and still come out to be the champ. Kung Fu warrior in the example that we were following. Okay, so that's one thing. It's long. It's long, lots of graphs. I know you don't like that. The technical issue with circulation is it's part of cardiovascular system. So you can't really divorce heart from circulation. Yet Guyton treats it as a separate whole chapter unit with multiple chapters in it. Some of the books actually discuss cardiovascular together, but since we are obliged to follow Guyton, as this is the prescribed textbook for your university, we will stick with that. However, the challenge obviously is you have already done heart physiology, and cardiac cycle you should revise before you start my formal lectures, which will be uploaded in sync with this level 0 video. From 1, 2 and 3, they will be numbered like that. This is 0, then 1, 2 and so on. So do revise cardiac cycle. It will give you a sort of base, a sort of platform to pick up proceedings and connect them to circulation. So that's the interconnectivity from heart is unique to this. Rest of the units in the entire book, they are independent. Well, in the sense independent that from a studying point of view or a teaching point of view. Of course, everything is connected. Everything is in the body, and hence everything is under some sort of a regulation and some sort of a coordination with other organs, other organ systems. So in that sense, no, everything is integrated. But in cardiovascular specifically, these two big units, they're actually connected even in learning and teaching. So the perceptive students, the ones who would do it properly, will find themselves going back and forth, especially from the cardiac cycle and then coming back to circulation. Having said all of that, I will make a conscious effort that you don't have to go back and forth a lot. I mean, by all means, if it improves your learning, certainly. I'll be giving references of heart physiology wherever they are required, inshallah extensively. I might even explain some of the heart stuff because it will augment our understanding of circulatory concepts. So now let's start with level 0. Again, I keep looking over here because I have some stuff jotted down here. So I'll just look at those points. Number one is multicellular organisms require a sophisticated, closed cardiovascular system, vascular system. Now, if you can just come to the circulation side of things, why is that, if you think about it? So once again, human beings have a very developed, you must have studied it in A-levels and FSC and metric, and even before that, that we have arteries and veins and capillaries and all those sort of things. They form the entire circulation, right? Why do we have that circulation? Why can't we be cockroaches? Life would be simple, right? It would just throw the white stuff around. You know, the blood of cockroaches is white. Some humans, unfortunately, have white blood as well. This can be said very nicely in Urdu, but I won't. You know what I'm saying. We have a sophisticated, closed, very intricate circulatory system. Why is that? Think about it. It all comes to distance. What is this distance bit? So the vasculature is situated in a way that it is optimally close to the nearest tissue. obviously in the middle you have the interstitium. By what I mean by optimal, the distance of a feeding artery to its target tissue, the one that would take nutrients and oxygen from this artery and give the metabolic waste back to it so that it's taken away. This is the tissue, this is the vessel. The distance between these two is optimal, and it's constant, and it should be constant. Any derangement in this system, so for example, if fluid comes and gets in between the interstitium, you have all sorts of problems. There is a small stat, you know, oxygen. Oxygen is required by all the tissues, right? It comes from your artery, and this is the tissue. Tissue requires oxygen. The supplier is the nearest vessel. Now check out the distance issue here. Why you need a sophisticated, developed, far-reaching circulatory system is when oxygen molecule comes in the blood, tissues cannot go and pull it. There are no active processes by which oxygen can be sucked into the tissue. You know, it's the good old diffusion process that causes oxygen from a higher gradient, higher level. There's more oxygen here, and this is obviously using up oxygen, so you will always have a relative lesser oxygen in the tissue because it's using it constantly. So there is a gradient that forms, and oxygen will always favor from higher to lower gradient. You have studied this in physics all your life, okay? Now, you know that one of the factors of that affect diffusion is distance. The distance that this molecule is required to traverse. If you make it shorter, diffusion is more. If you make it longer, it affects diffusion in a bad way. So the molecule requires more time to diffuse very quickly. Most of the distance, this is fascinating really, they looked this up as well. The distance between tissue, the optimal distance between the tissue and the nearest vessel is in micrometers, okay? I have these stats here. It takes about, the optimal distance is about within 100 micrometers. It takes about 5 seconds for oxygen to go from the vessel into the tissue. 5 seconds, still 5 seconds, right? If you were to increase this 100 micrometers into 1000 micrometers, that is 1 millimeter. What is 1 milliliter? 1 millimeter. If you can look at the scale, it's a very small, minuscule distance. So you increase from 100 micrometer to 1000 micrometers, which still is very small, which is a 1 millimeter. You know the time now required for oxygen, the same oxygen molecule, to go from the vessel to the tissue increases up to from 5 seconds to 500 seconds, which is about 8.3 minutes. 8.3 minutes, while it was just 5 seconds when you had the optimal distance. And if you were to, just for argument's sake, increase this distance between the tissue and the vessel to 1 centimeter. 1 centimeter also is a very small distance, right? It's bigger than 1 millimeter. So if you just change the 1 millimeter into 1 centimeter, it will require 50,000 seconds for this oxygen molecule to hit the tissue, which is about 14 hours. So this is why you need a very specific, far-reaching, sophisticated system, circulatory system, so that all the tissues are within reach of the vessels. So that's one thing. Second is, I have changed my sequence of the lectures which I usually have been giving over the years. So lucky you. This is the beta version of the new lecture series. Okay, here it goes. You need to conceptualize circulation. If you invest in understanding the overall architecture of circulation, you'll be much better off when you will learn or when you will try to understand a specific detail. You know, it's just like Google Map. I'm giving you an example. In Google Map, when you are zoomed out, it's always good to know which area you would like to explore on your electronic Google Maps, right? If you are given a zoomed in view of even your own house and your own street, you may never recognize what street it is. Yeah? But if you are given a reasonable zoomed out, I'm not saying at the world level or the planet level, okay? I'm saying, well, province level, even country level, zoomed out image if you're given it, you'd be able to navigate quite nicely how to get to your house or your street. So we are now zooming out. We are going away from the detail. And this is the zoomed out version of the cardiovascular system. So I am involving the heart, as promised. You have a lawn in your house. If you don't, I don't. Doesn't matter. I have a few plants. I can call them a lawn. You must have seen a garden. You must have seen a lawn, right? Imagine you have a lawn. You have to water the plants, okay? Now, you take, say you are standing on the edge of your lawn, okay? And you have to water the plants. Now, there'll be plants which are closer to you, and then there will be plants which will be farther away. You take two types of pipes, rubber pipes, as a supply of water, okay? You connect one with one tap and the other piece of pipe with another tap. There's a difference, two differences rather. One pipe is thinner in its wall and of big diameter, big caliber. It's a big diameter pipe, but the wall is moderate, it's thin. That's one piece of the tube that you will use. I'll tell you where would you use it in your lawn, all right? The second pipe is thicker in its wall, and hence the caliber, the space inside is smaller. So one, you have a big caliber, big diameter pipe with thin walls, and the other is a smaller but thick walled rubber pipe. So you have two pipes. You will use the smaller, more muscular tube to water smaller plants or nearby plants. You can even use it, the jet feature. You just constrict an edge, the terminal edge of this tube, to make water jet out, because it's the way it's structured. It's muscular, it's tighter, more firmer than its flimsier cousin, the other pipe. The other pipe, since it has a big caliber, the water supply through it is more than the thinner pipe, okay? So you may use it to water distant plants, or even use the water that is in there. Sometimes you just pick it up like this. It acts like a reservoir of water, and you always have water in such pipes, okay? Secondly, the water source of the bigger pipe is slow. The water source of the thinner, more muscular, not the small caliber, thick walled pipe is fast. It's high pressure. That's why you needed a thicker wall to withstand the pressure from the water source. And here there is no high pressure, so it's all right. That's a big part of our explanation. Now all you need to do is look at my hands. This is that big caliber pipe. I have it in my hand like this, okay? And this is the thin, more muscular walled pipe. I have it in my hand here. They are pipes, right? So you just connect them from top and from the bottom. You have connected both the thin-walled big diameter pipe here and the thick-walled small diameter pipe here. Okay, let me show you the difference so that you are clear on the diameters. Okay, you took these tubes, connected them on top, connected them from the bottom. Done. Now you have a closed circuit pipe system. It's not one pipe, you know this. There are two different pipes, and you've connected them on the top and on the bottom. Now take whatever kind of juice you like, fruit juice. Drink the juice. When the box of the juice is empty, try to fix it on the top where you joined the two tubes. So pull them apart, put the box in there, and now connect this pipe on one side of the can or the box and the other into this side. So all I've done is I've introduced a box between the upper two ends of the tubes. That's what I've done. I hope this is clear. I'll be showing the picture of this setup when we'll go to level 1, but we are at level 0 right now. Okay, so you need to use your imagination. So you have a box, a tube coming out of it, the small caliber tube, and a big caliber tube is going into it. I have given you extra information. Small caliber tube coming out of it and big caliber tube going into it. So clearly I'm taking you somewhere here. Now at the bottom where you temporarily connected it, you can keep it like that, but at the small caliber end you take any hairpin or hair clip. Ask your mother to give you one, or your sister, or if you are a girl, you would have your hair clips, right? Just put your hair clip on this tube like this, so that it's narrowed a bit. No technical words. It's narrowed a bit. Okay, it was like this, going into a bigger diameter tube like this, but you have introduced a clip here so that it's constricted here. Khalas, finito. This is the setup. So once again, I'll just repeat. You have a box, one hole here, one hole here. From this hole, you have a small caliber tube running down to this place where it is being constricted by a small constriction device, in this case a hairpin. Somehow you have fixed it like this, okay? And this then carries on to the big tube, bigger diameter tube, and which goes back to the other side of the box and enters into it. If this is clear. Now introduce water in this whole closed system. Just fill it with water. Don't fill it in a way that it distends any tube or the box or disturbs the clip. Just fill it with water, nothing else. If you've done that, your cardiovascular system is ready. Voila! How is this cardiovascular? If you've already not worked it out, what we've done in a very simplistic way is the box represents the heart. The thick-walled, small diameter tube represents the arterial side of circulation. And this tube, the thin-walled, big diameter tube, is the venous side of circulation. Obviously, it's a simplified version. What's the paper clip? It's on the arterial side, right? This paper clip represents, if you said arterioles, you're right, arterioles. This is where you get to constrict the arterial side of the system. Okay, you can constrict the entire arteries if you would like, but the most of the constrictor technology is here, right here, at the level of the arterioles. It's basically, arteries are big, we call them big arteries, then they divide into small arteries, then they come in and become the arterioles, and then they form the capillaries. And the capillaries then form venules, and then small veins, and then large veins, and so on and so forth. So this is the system. We have now labeled it as the actual cardiovascular system. We filled it with water. Water is blood. Okay? In a living human being, this stuff is dynamic. Blood moves through the cardiovascular system. Do you think blood moves on its own? It's a big and interesting question of physics. If you were to, if you want this water in this closed system that you created, if you want it to flow, it won't flow. It can never flow unless you push it. You have to push it. Okay, how do you push it? Take a balloon, leave the system for a bit. Take a balloon, fill it with water, then squish it like that. The balloon, the water balloon, okay? Don't squish it so that it bursts in your face. Obviously, don't do that. But squish it a bit. What will happen? What are you doing? This balloon is closed circuit, right? It's tied, it's closed, and it has water in it. It's comparable to what you have just created. So you are basically applying pressure by squishing it. You are increasing P, pressure, on a closed circuit system which has a known volume of fluid inside, V. You are changing P, delta P, change in pressure. Change in pressure is leading to, pressing upon a fixed volume of fluid inside this balloon. Now, from your extensive experience of squishing balloons, you would know that water will try to readjust as pockets, as clumsy pockets of balloon outside your fingers. Within your fingers, here it will pop up here, it will pop up here. It will readjust itself because it can't change its volume because you've sealed it, right? It will readjust itself to distribute or to deal with this delta P that you have created by squishing it. If you've understood this example just on the face of it, let's just come back to the tube and the whole box and all that. Now, if in the box you introduce a piston, a piston-like device. What is a piston-like device? A piston-like device is, I don't have any objects here. It's like it has a front like this, and a machine here which pushes it. So this is the face or the plate or whatever, and there's a machine which is connected with electricity or source of energy, whatever, and it will push this front like this. So if you have water here, now water here, you have just introduced a piston in between, inside your box, remember? And now you apply pressure. You are applying delta P. Yes, delta P. You're now applying delta P, and you push the piston, which pushes the water towards the arterial side of the circulation. Unless you do this delta P thing, your blood will never, or your fluid will never flow in your closed system. So actually heart, this is a nice one-liner, the heart provides the delta P. Heart actively contracts. It actively contracts. It is providing the delta P, the piston-like effect, which moves blood through a closed system. Okay? So now you have a situation in your example, where a piston now is pushing at a regular interval. Let's say it has just pushed it once. Just keep it simple. You turn the machine on, the piston moved, you switch it off. So the amount of water it displaced out into the arterial side or the thick-walled small caliber tube. This displaced fluid will displace the fluid which it will encounter in the tube further up. And then literally like a wave, it will travel down because you have created it. You have disturbed it. You have disturbed the quiet equilibrium of fluid inside a closed system. You have produced a wave. That's the word. You have created a wave. So now this wave will travel, the pressure wave. It will travel down. It will come to the pin-like constriction that you created. And then it will pass over into the broader tube system. Okay? The pressure in here will decrease as the fluid or the pressure wave comes down. Why? Friction. No system is perfect. If in a perfect system with zero friction, something that doesn't exist in real life, you would not have any decrease in the wave pressure. But since you have a tube and the tube has a wall and the fluid will have friction with this wall, as you go along, energy will be dissipated and this pressure wave will decrease. Now it goes over into in the broader tube and tries to go up and comes back actually. What goes around comes around. So for example, let me explain what I've just said in one line. Say for example, the movement of the piston moved 5 ml of water down this tube. Guess how much water will be instantly credited back into the box? Voila, 5 ml. Not the same 5 ml. It's a different 5 ml. But since you have water filled in this closed loop system, any movement, any disturbance, any wave that you would create would be transmitted down, up and back again. What goes around comes around. So 5 ml displaced from here, 5 ml comes up again. It's a closed system and water is filled with it. If you've understood this, you will understand Frank-Starling law. How? What is Frank-Starling law? Frank-Starling law is whatever comes to heart is heart contracts it forward, i.e. preload is directly proportional to cardiac output. Yes, it's okay if you don't exactly follow what I've just said. I'll explain it. The amount of blood that comes into the heart, Frank-Starling law says the heart will accommodate it and then contract proportionately to its volume to propel it forwards. This is the Frank-Starling law. This is the direct proportion between preload, the amount of fluid that comes in, or blood that comes into the heart, and cardiac output, which is the output of the heart. So in the tube system, what did you do? You pushed 5 ml outwards and exactly 5 ml came back. This is what happens in a closed circulatory system in the human body. The heart constantly is pistoning out, pushing out blood, and instantly is being credited with blood, more blood of a different kind. Obviously, you know the difference between deoxygenated and oxygenated blood. But the system is closed. You now understand it's a film of blood that is filled in the circulatory system. One big film, one big unit of blood that is moving around. It's not segments. It's just one big sophisticated circulatory system, yes, no doubt, many branches and whatever. But the basic concept is of these tubes. What you push is what you get. I hope this is clear. I can see that the length of the video has again gone up. What I'll do is I will divide this level 0, if it can be divided, not mathematically, into 2 parts. This is part 1, you can consider it part 1, and part 2 I will record another video just for convenience. Very quickly, the summary is we discussed the need of a closed circulatory system in multicellular organisms, human beings, and lower mammals as well. And number 2, we studied you can say the architecture of the cardiovascular system and what it is and so on and so forth. In this, I forgot to mention one thing. I can't take retakes. I don't know how to take retakes, so it's really live what I record. I did miss one thing. When we had set up all the tubes and the box and the hairpin, and we filled it with water, just so that nothing is dilated, okay? It's just enough water to keep the tubes patent, not dilated, no pushing, just filling. You need to just take a reading of the pressure that water is exerting at this point when nothing is moving. You've just filled it with water. Just take a pressure reading from the water that it's exerting on the walls of the tubes. Let's say, call it filling pressure. I smile because I'm luring you into a difficult concept, but in segments, in easy steps, baby steps. Just call it filling pressure. Remember this. We will talk about it later on, filling pressure. And then you move the piston and all that stuff. So just slot it in the initial bit of the lecture, inshallah. Okay? So I'll be recording the second part of level 0, and it will be all uploaded in one go, inshallah. Okay, take care. Assalamu alaikum.